Let's begin. And just like this morning, okay, so now it's my turn to talk. You guys have a lot of time here. Now it's my turn. So just like this morning, everyone in the class got this. That's awesome. Imagine a place in the cosmos far from all gravitational and frictional influences. Suppose that you visit that place. Just suppose, I don't want anyone to go there. And throw a rock. The rock will, everyone said, continue in motion in the same direction at constant speed. Because you all know Newton's first law that says, objects in motion stay in motion. Okay, now let's see if you know what that really means, because that's what question number 2 is. And the answer is not so much. 3 of you got it right. The correct answer here is 0. Allow me to explain. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed in this direction? Objects in motion stay in motion. How much force is required? Big fat 0. Objects in motion stay in motion. So what does that mean? It means that a force is not required to keep an object moving. Rasmus, you should be listening now. Okay? Now you might say, Mr. Bennett, I know that when you push on the scale across the floor, it's going to come to a stop. How come? Because there's friction. Right? But the question is how much net force. So in other words, if there is, I don't know, let's say 10 newtons of friction, or minus 10 because it's that direction, that means you have to keep pushing with 10 newtons. Braden, you're not listening. You're doing something else. You're not listening. You're not learning here. Listen to me. What did you write down? You're writing that down? It's looking like you were talking to him. Listen and watch. Okay? Okay. So the forces are balanced. The net force is here. What's the net force? 10 and 10, they're balanced. The net force is 0. If the net force is 0, objects in motion stay in motion. But unfortunately, there's almost always what involved? Friction. But the question says, how much net force? Not how much force, how much net force. Little trick. Okay? Does that make sense to you? Give me the nod of agreement. Okay, question number 3. Mac and Tosh, pause for laughter, are arguing in the cafeteria. Mac says that if he clings the jello, and don't do that, with a greater speed it will have greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. And who do you agree with? Explain why. And the correct answer is B, Tosh. Inertia is based on mass. Okay? If you have inertia in motion, that is called momentum. That is called momentum. Great, you shouldn't even have your clicker in your hand anymore because you're done with that. Do the listening part now. Inertia. Inertia in motion is what we call momentum. Okay? The inertia is simply the mass. It's another way to, it's really hard for me to describe, but it's basically the mass. Bigger things have more inertia. They're harder to either start moving or stop moving. Okay, are we good? The answer is B. Okay, question number 4. Suppose you were in space in a weightless environment. Would it require a force to set an object in motion? If I was in space and I had my sleeve of tennis balls with me, would it require a force to move the tennis ball? Yes. And the answer is, did you get it right? Yeah, the answer is yes, of course. Right? Because the tennis ball is at rest and you want to move it, so it takes a force. Right? Forces cause accelerations. A change in motion. Okay, so the answer is yes. Number 5. Fred spends most Sunday afternoons at rest on the sofa, watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Explain. Does it increase his inertia, decrease his inertia, or it has no effect? And the answer is A. Why is his inertia increased? He's gaining weight. He's eating chips and he's sitting on the couch. Two things that are guaranteed to increase your inertia. It's the tendency of an object to keep on doing what it's doing. Okay? Big things are hard to start moving, and they're hard to stop moving. That's what it is. The tendency of an object to keep on doing what it's doing. I get it. Inertia is hard for me to explain too, because why don't I just say mass, right? That's what it is. The tendency of an object to keep on doing what it's doing. I mean, could I give you a scientific definition? Yeah. Let's Google it up and see what we get. But I guarantee you that mine's is easier to understand. Let's see what we get. Yeah, I guess, man. Learn to go at lunch. Inertia, a tendency to do nothing or to remain unchanged. From physics, a property of matter by which it continues in its existing state of rest or uniform motion in a straight line, unless that state is changed by an external force. That's kind of what I said, right? Alrighty, number 6. Ben Too Close is being chased through the woods by a bull moose, which he was attempting to photograph, or ride, perhaps. I don't know. Remember that? Yeah, remember that a few years ago, right? Guy was on a boat, trying to jump off the boat and ride the moose. Bad idea. Okay. The enormous mass of the bull moose. The enormous mass of the bull moose is extremely intimidating, but it then makes a zigzag pattern through the woods. He'll be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. Okay, so you have 3 choices. The correct answer is A. First of all, the moose has more mass, so he has less inertia. Is that true? No. The moose has more mass, so he has more inertia, so he's not able to make zigzags as easy. Can large things change direction easy? No. It will not work. The moose is still able to make a zigzag pattern. Your best answer is B, I think. Okay? Same principle is true in football. The running backs tend to be smaller. They're quick. They can make quick changes in direction. Linebackers are generally larger and can't do that. The Titanic is another good example. The Titanic was really big, hence the name Titanic. And so it sees the iceberg. Is it able to change its direction quickly? No, it has a lot of inertia. Can't change its motion. Question number 7. 2 bricks are resting on the edge of a lab table. Surely she's short, stands on her toes and spots the 2 bricks. She acquires an intense desire to know which of the 2 bricks are most massive. Since Shirley is vertically challenged, she's unable to reach high enough and lift the brick. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So, she can only reach high enough to give them a push. Can't lift them. The brick that moves more has more inertia and is heavier. The brick that moves more has less inertia and is lighter. Both bricks move the same, feel the same, and move the same distance. Well, for sure, C is wrong. The brick that moves more has less inertia. Is that right? The one that moves more has less inertia and is lighter. I think the answer is B. Indeed it is. Jared, are you watching? Why do you have a device out then? No, I don't. I want you to listen. Okay, these next questions are important, you guys. So if you haven't been giving me 100% attention, you need to start. Guy's name? Out below. Thank you. Thank you. I'm here all week. All right, so look out below. Now, before I go any farther, this is fiction. No actual cats were harmed in the making of this question. This is not a documentary. Okay? All right, so here's the physics part where you got to learn, you guys. Look out below drops an approximately 5 kilogram fat cat, weight of 50 newtons, off the roof of his house into the swimming pool below. Upon encountering the pool, the cat encounters a 50 Newton upward resistance force, assumed to be constant. Use this description to answer the following questions. And here's the cat right here. Which one of the velocity time graphs best describes the motion of the cat? Support your answer with sound reasoning. And the answer was, who got it right? Oh, lots of you got it right. That's good. Why is it B?
Because it's going down and it's not.
And speeding up, exactly right. So here, now if we were to draw a picture on the side, which you guys should, okay? So for the first part of the trip, the cat is accelerating. Callan and Braden, you guys are not watching and you're not going to understand this later. You must listen. I still need you to listen. It's pretty easy to guess. It's a 33% chance you're going to get it right. Do you know why, Callan? Do you know why? Okay, then maybe you should listen. So when the cat is accelerating, what is the net force on the cat? Well, it's minus 50. 50 newtons down due to gravity. Gravity pulling the cat down, and the cat, just like the tennis ball, will accelerate, right? Speed up. Okay. When the cat hits the pool, which happens right here, now you've got 50 newtons down and also 50 newtons up. How come? Water resistance. Yeah. And now what's the net force? Zero. Balanced. 50 down, 50 up. So when the net force is zero, that means the acceleration is zero. No longer changing speed. Not speeding up, not slowing down. Constant speed. How do we show constant speed on a velocity time graph? With a flat line. With a flat line. Now, why is the graph below? Why is it down here? Because it's going, the velocity is down. The cat is falling. Down is negative. The cat will fall through the water at a constant speed until it touches the bottom of the pool. And then Luke will jump in and rescue the poor cat. Yeah? Okay? A lot of people want the cat to slow down or something like that. If the cat were to slow down, what would it look like? It'd be like that, right? Why is it not this one? Because here the velocity is positive and above. So it's definitely not that one. The only one that you might get away with would be that one, but that's not one of the options. Alrighty, so number 9. Which of the following dot diagrams best describes the motion of the falling cat from the time that they are dropped to the time that they hit the bottom of the pool? The arrows on the diagram represent the point at which the cat hits the water. Support your answer with sound reasoning. So this is that ticker tape thing again, right? Coming back to that. So we know that the cat is accelerating, so that means the dots need to be further and further apart. Which one is that? Well, that's either A or C, not B, because there the dots are the same distance apart. And then we know that the cat moves at a constant speed. C here, they get close together, so this one slows down. So the correct answer is A. No, it does not. We've already gone through that T right here. The forces are balanced, which means the acceleration is
So we don't pay attention to any of the velocity after it hits the water.
It stays the same. If the cat hits the water at, say, -5 meters per second, he continues to go through the water at -5 meters per second. Now, is that what happens in real life?
No.
Probably not. How come? Because the resistant force is considerably more. But in this case, the forces are balanced. The forces are balanced. Well, clearly it's not real life, because nobody would throw a poor cat off the roof, right? So, you gotta read the question. So the answer was A. Okay, now, here's the next 3 questions, 10, 11, 12, 13, the next 4 questions are the key ideas for the day. So listen carefully. I know you've been giving me your attention for the whole period. I need about 6 more minutes. Okay, so listen carefully. Several of Luke's friends were watching the motion of the falling cat. Being physics types, they were students of mine. They began discussing the motion and made the following comments. Indicate whether each of the comments are correct or incorrect. Support your answer. You need to know these. Once the cat hits the water, the forces are balanced and the cat will stop. That is false. Why is it false? Is this part true? This part is true, but will the cat stop? No, that part is false. And because it's an and statement, Jared, right? Connor, another Adam, Travis, Raston, Braden, a few computer science people, and Josh. It's an and, right? You got to have both have to be true.
I don't.
Little crop. Don't understand this? You're talking about this cat.
Well, you're talking about.
Oh, I'm talking about and statements in computer science. When you got to have this and this. And Murtaza, yeah. And, right? Okay. Listen carefully. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. This is false. Why is this false? False, because the forces are balanced. The forces are balanced. The F net is 0, which means the acceleration is 0. The cat speed stops changing. The cat does not slow down in this situation. In real life, quite often the force up is greater. But that's what they told us. It said 50 down, 50 up. That's what you can only go by that. Okay, I think I hit pause there, so I'm going to leave that up there. The reason the answer is false. Okay, let's go look at number 12 here. Upon hitting the water, remember, this is this situation, right? Upon hitting the water, the cat will bounce upwards due to the upwards force? No. No. False. The cat is, what does the cat do? No, does not slow down. He stops accelerating, and there is a difference. Right? The velocity remains the same. How come? Because the forces are balanced. I feel like I've been repeating myself today. Have I, Connor? Do you know why? Trying to get people to understand. The cat stops accelerating. The velocity is constant, which means doesn't change. Number 13 is, if you're going to put a star beside anything, this is the one. This is the pinnacle of knowledge for the day. This is the thing you got to get. This is it, the granddaddy of the day. If the forces acting upon an object are balanced, then the object A must not be moving, B must be moving with the constant velocity, C must not be accelerating, or D, none of these. I will tell you this, the morning class, nobody got it right. Correct answer is C. A couple people got it right. Okay. Why is it C? Listen, and then you can write some stuff down. Listen. Why is it C? So, if the forces acting upon an object are balanced, so whether it's a fat cat with gravity of 50 newtons and a water resistance of 50 newtons, or maybe it's two guys pushing and pulling on a both with it. Does it have to be 50 newtons? No, any number, right? As long as they're balanced, if the forces acting upon an object are balanced, then the object must not be moving. In other words, it must be at rest. If the forces are balanced, does it have to be at rest? No. For example, car sliding down, or cruising down the highway at 100. Air resistance, force of the engine, right? The forces are balanced, right? There's still that force. It is moving. So it could be moving, right? So must not be moving? Not true. Could be moving at constant speed. Could be moving at a constant speed. Adam, did you write that down? Do you not understand? This is the important part of the day. This is it. You must get this. Focus. Yeah? It's that it could be. It could be at rest, or it could be moving at a constant velocity. So, in part B, when it says must be moving with a constant velocity, no, because it could be at rest. It could be doing either one of those things. So it's C, must not be accelerating. That is true. If the forces are balanced, then that means then that the net force is 0. And if the net force is 0, that means that the acceleration is 0. If the net force is 0, the acceleration is 0. If the forces are balanced, it must not be accelerating. Big star. Okay, you have a few minutes left. If you did not finish